Si tu l'utilisais,
I should mute or unmute.
Tu as commencé l'enregistrement?
Oui. Okay, you can.
Okay, thanks. I'm Christian Merten. For those of you that don't know me, I'm a PhD student of Johan Common, based in Utrecht, and I'll tell you a bit about algebraic geometry in Lean's library mathlib. And with mathlib we've already heard today. But let me start with saying what this algebraic geometry is about. And so what is algebraic geometry? Well, classically, it's the study of zeros of polynomials over some field. So we're interested in objects of this form, sets of this form, taking x and kn, where they that are the common zeros with some family of polynomials over k. And well, in the 1950s and 60s, Grothendieck reformulated this study of zeros of polynomials in the language of schemes. And what a scheme is not really important. But instead of studying this set, we're now studying its ring of rational functions. So we're studying this ring instead of this set. And this ring is, in this case, the ring of rational functions on this set. And there's a general construction that sends such a ring to what we call an affine scheme. And this construction is this spec factor. And affine schemes, by how they are defined, can be completely understood via commutative algebra. And it doesn't matter how this precisely works, it just matters that affine schemes are an object that are easy to understand from just studying rings. And a scheme is now a geometric object that locally looks like an affine scheme. So like a manifold looks locally like a Euclidean space, a scheme looks locally like an affine scheme. And so we are studying objects that are geometric objects, and the challenge is to mostly do the study of these objects in the language of rings instead of the language of some complicated geometric object. So let me tell you what I want to talk about. I want to give you a bit of history of algebraic geometry formalizations and give you a library overview of what we have in mathlib, and then focus on two design decisions, the definition of schemes, and then I'll talk a bit about this topic of reducing it to problems of commutative algebra. Okay, so I'll start with a bit of history, and I think the first formalization of affine schemes was in 2003 by a PhD student, Chikli. I can't access his PhD thesis, so I didn't verify my claims here. What I've read is they have formalized affine schemes in ROC, but they didn't formalize schemes. And yeah, so then 2018, so 15 years later, a first definition of schemes was done by a group of Kevin Buzzard and two undergraduates at Imperial College. And they, well, formalized schemes in Lean 3. And then 2 years later, this definition of schemes actually enters mathlib, but in the version Lean 3, so in the nowadays called mathlib 3, with some more contributions by other people. And there's a paper of the 6 people that are listed here on this story, and I won't go into the details of the story, but it's a nice read. And then we had the definition of a scheme. But the definition of a scheme is just some geometric object. Of course, we want to know something about these schemes. And so in 2021, somehow unrelated to the scheme story, elliptic curves were added as cubic equations. So it's 5 tuples of elements of some ring, completely unrelated to schemes, by David and Kevin. And then the same year, right, in 2022, there was a definition of schemes in Isabelle, which doesn't use dependent types. So a nice showcase that schemes can be formalized in Isabelle without using dependent types. And at the same time, Andrew Young, who's also here, succeeded to construct fiber products for these schemes. So for the people that don't know what fiber products are, it's just some categorical construction, and it's somehow the most fundamental tool you use in algebraic geometry. Without fiber products, you can't do anything. And so constructing fiber products is not so straightforward. So there's some proof going into this. And this is really what enables you to do algebraic geometry. Before that, you can't do anything. And then in 2023, the port happened from Lean 3 to Lean 4. So for a year, nothing happened. So the definition was ported and progress stalled a bit. And then in 2024, I can list many, many things. Many things happened. We had a workshop on formalizing algebraic geometry. I'm just listing one project here because I was personally involved in this project. But for example, we got evaluative criteria for the people that don't know what this means. And so we got a lot of progress. And in 2025 is now, so I'm going to tell you what the library looks like now. Okay, so the obligatory slide on a word on Lean and mathlib. I think by now this is not news to anyone. So Lean is a dependent type of interactive theorem prover, and mathlib is the library that we've already heard about by Michael before. It's a user-maintained mathematical library, and in particular, we are relying heavily on the fact that we already have a treatment of topological spaces well developed in mathlib. We are relying on the fact that we already have a well-developed theory of commutative rings in mathlib that we can use. Okay, and also I want to say that I'm just one contributor to this algebraic geometry library in mathlib. There are many, many people that worked on this. I'm just listing a few of them here, and I certainly missed someone, but those are the ones that significantly contributed to mathlib algebraic geometry over the past years. And to point out one specific topic, elliptic curves, that I won't really treat here because I want to talk about more the theory of schemes. But elliptic curves are mostly developed by David and Junian. And then the scheme library has really mostly been developed over the years by Andrew, and then recently also by myself. Okay, so let's tell you what we have. And this is maybe a slide for the algebraic geometry experts or the people that know some algebraic geometry terms. So I'm giving a list of things that we have. And for the people that know what the things mean, I hope that's somewhat useful. So we have limit properties of the category of schemes. So we have fiber products, as I already said, with co-products with some inverse limits. We have the group law on elliptic curves, which is really a nice result because associativity of the additional elliptic curves is quite hard to show. Then we have a bunch of properties of morphisms, essentially all the standard properties of morphisms that we could find in a standard textbook. We have the evaluative criteria, which is a nice achievement also in 2024. We have ideal sheaves, which is maybe for the people that know what quasi-coherent sheaves are. It's a special case of quasi-coherent sheaf, but the reason is that we have this is because we don't have quasi-coherent sheaves. And this is probably surprising for the people that know what they are, but we don't have quasi-coherent sheaves, and you can do some algebraic geometry without quasi-coherent sheaves. It's surprising, and if you read EGA, that's not what the impression you get, but you can do something. And so we have ideal sheaves as a mild replacement of that. And then we have some basics of cohomology theory. So we have some sites, a risky site, a tile site, etc. Okay, so let's get to some more formalization things. And well, we have also some concrete things like projective space. Namely the definition of schemes. And since Cyril earlier gave the talk about hierarchy builder and mentioned all the different design patterns about bundling and unbundling and semi-bundling and packed classes design and so on. This is maybe an interesting example. This is completely bundled. And the reason why I asked earlier this question, because you said in rock and math class, I think the only exception to this unbundle everything was algebraic varieties. Well, algebraic varieties are somehow a special case of schemes. And so I'm assuming it's for the same reasons. So again, we have schemes as a bundle type. And it's a special case of a locally ringed space, whatever that means. Just think of a geometric object. And it's precisely what I've claimed it to be. It's a geometric object that locally, so for every point, there exists some neighborhood such that the restriction of X to U is isomorphic to the spectrum of a ring. So it's an affine scheme. So it's precisely a geometric object that locally looks like an affine scheme. And it's completely bundled. And so to introduce a scheme, we write this variable X in scheme, very, very simple, very concise. And where the main reason why we bundle everything here for schemes, and if you remember Cyril's talk, he said that mathlib generally doesn't bundle things. And the reason why we bundle things is because many arguments are of categorical nature. So we, for example, I mentioned that earlier, we use fiber products, and there's no concrete construction of the fiber product of schemes, but there is an existence proof that fiber products exist, and then we can use the universal property. But this is all phrased in terms of category theory. So it's very convenient to be able to use this here just seamlessly. Yep.
Why non-empty rather than just the equivalence?
Oh, because exists expects a prop. So the ugly thing you can write is exists, this isomorphism, comma, true.
And you don't want a sigma. You really want a distinction.
Yeah.
I just want, yes, I just want an assertion that there exists an isomorphism. I don't want to bundle an explicit choice of isomorphism. Yes. Okay, and just to contrast this with a, yeah?
I'm similarly wondering, like, is it fine to just assume that this open cover exists, or do you also want to bundle a choice? Coming from differential geometry, we definitely bundle a choice to everywhere. This matters.
Right, we don't bundle choice. I think this makes things easier. I claim this makes things easier. But I know algebraic geometers like charts. But yes, there are no charts in this picture. It's just a proof that it locally looks like an affine scheme. And this is really everything we need. But to contrast this with what you just mentioned, differential geometry. So the differential geometry library to introduce this manifold is these 5 lines of code. I'm not putting this there to make fun of the manifold library. I'm putting this just to contrast it with the design of schemes. For schemes, we write variable X in scheme, and for manifolds, we write this. And this has a big advantage because all of a sudden we are now in this unbundled world. And as Cyril said, mathlib is generally developed in the unbundled style. So this much better fits the rest of the mathlib design. So in particular, a manifold is automatically a topological space, or what I should rather say, a type that is equipped with a manifold structure is also equipped with a topological space structure. And every lemma about topological spaces will expect a type together with a topological space structure. But if I have a scheme, then my scheme is not a type. It's a term of type scheme. And so I can coerce that scheme into a type by considering the underlying type. But that's an additional conversion that I have to do. And this causes some friction, but I think overall it's good that we're doing this in this way because of these categorical arguments. I think there's no real way to do this in an unbundled way without using, if we want to use category theory. Okay, so that's the definition. And let's now talk about maybe the main design problem in algebraic geometry is that I told you affine schemes are always of the form spec of R for some ring. For some construction, we don't know how it looks, but they're always of this form. And every scheme locally looks like an affine scheme. So this is the only thing we know. It's a geometric object that locally looks like some object that we understand from commutative algebra. So every proof should reason via reducing the problem to a problem about commutative algebra. There's no other way we can reason about schemes other than reducing it to commutative algebra. And this reduction to commutative algebra is tricky. And just to give you some idea of how this looks in the literature, because we're in France, I picked an EGA quote. So I translated for the people that don't speak French to show one. Let us note that the problem is local on X, so we may restrict ourselves to the case where X is affine. That's very nice proof and very nice introduction to the proof. And if you're familiar with algebraic geometry, this is perfectly fine. This is a good proof. And the reader often doesn't expect more details. It's typically clear how to reduce to this local case. But unfortunately, the notant que la question est locale sur X, that's not a tactic in Lean. So, so it doesn't work, unfortunately. Another example, so it's not only the French that do this. In Hartshorne, now we can replace Y by an affine neighborhood, and so we may assume that Y is affine. Well, also good proof, but unfortunately also this is not a tactic. And another thing that is slightly different nature, but similar way of reasoning. So we have some proof about Nagata schemes, whatever that is, but then they say, let spec A be U, be a subset of X, be an affine open containing Z. Well, also very innocently looking line of proof, but let me start with this last quote. So what is an open subset of a scheme? Well, an open subset of a scheme is certainly not a scheme, because the type of an open subset is set X or opens X maybe, but it's certainly not scheme. And so because we're bundling everything, a scheme cannot be equal to an open subset. The underlying type could be, but a scheme cannot be equal. And so in particular, this statement, which is a reasonable statement that you would see in a typical line of reasoning in algebraic geometry, that we have a scheme, we have some open, we know it's affine, so it looks like spec R. So then there should exist an R such that U is spec R. Anyway, this doesn't even type check because U is of type opens and spec R is of type scheme. And even if it would type check, it's the wrong statement because this is an affine open, so it's isomorphic to the spectrum of the ring. So at least there should be an isomorphism somewhere. And then we could make a statement that says U corresponds to a scheme, or the canonical scheme structure U equipped with its canonical scheme structure is isomorphic to the spectrum of a ring. That's a reasonable statement. But that adds two additional complications. Now we don't have a rewrite, so we don't have an equality, so we can't substitute this equality everywhere, and we have an isomorphism somewhere in the picture. So, well, one way of dealing with this is to develop the API not in terms of opens, but in terms of abstract open immersions. And this is quite nice. So instead of saying there exists a ring in com ring cat such that this holds, we could say that there exists an open immersion whose domain is spec R, and where the image of this open immersion is exactly U. And now we're talking about two opens. The statement one open equals to the other open makes sense. So this is of course it's additional friction, but this is quite a nice way around this. But for the other part that I showed you, so for these two quotes from EGA and Hartshorne, there's not really a solution. And well, I show you one attempt at the solution, or a few attempts. So what we have sort of, we have a notion of locality of some properties. And let's make this situation very simple, and let's take only a single scheme. If you have a single scheme, then we can say, okay, we have some property that is local. So we have some property P that goes from scheme to prop. So takes a scheme and spits out a true or false. And then it says that this property is local if we can check it on affine opens. Whatever, so we can say that P of X holds if and only for every U affine open in X, P of U holds. This is, we could define this property, and then we could do something like this. We could have some sort of, yeah.
Isn't it the same as saying P is open or something like this?
I don't know what P is open means.
As a set?
No, but P,
I don't.
Scheme, c'est.
I'm not sure.
Non, mais
I'm not sure how this is.
Tous les schémas, c'est pas.
Ah oui, okay.
Okay, the question is resolved.
Yeah.
So we can have some induction principle that looks very nice. So we could say we have a property of schemes, we know it's local, and so we have an arbitrary scheme, and let's show it. If we show it for every spectrum of a ring, then we can also know it for X. Well, because we take a cover of, or we check it on every affine open, and if the property is also stable under composing with isomorphisms or some unmathematical assumption, then we get that this property holds. So we can do something like this. This is not unreasonable, but the way that the textbook does it is much more powerful than this, because the textbook says la question est locale. So the problem is local. It's not saying one specific property is local, but it's saying the whole situation is local on X. So what does the situation mean? So what about properties that involve multiple morphisms and multiple objects? And now it becomes more complicated. And well, we can try to do it slowly and do one step at a time. So let's add one more object and one morphism. So now we get something that is local properties of morphisms. Okay, so we can say a property of morphisms can now be local at the source and the target, because now we can reduce it on both sides. And well, we can, for example, define this. So we can say a property of morphisms of schemes. So morphism property scheme is just a property that takes a function that takes a morphism of schemes and spits out a true or false. And then we can say that this is local at the target if and only if, well, we can check it on the cover. So whenever we have a cover of Y, an open cover of Y, then we can check it for this morphism F if and only if it's true for every restriction to these open components of the cover. So we get the map, if we restrict it to U on the target, we get a map F inverse U of U to U. And now you can already think about what it means for to be local at the source. And you will realize it's a different condition. Because restricting on the target and restricting on the source are fundamentally different. And so already here we need two predicates, one for the target and one for the source, and they are different. And all the API that we need to develop for is local at target, we also have to develop for is local at source. And then you get some reasonably nice proofs. So this is some lemma that is called foo, and it takes a morphism of schemes and proves that P of F holds. Well, it can't be a very interesting property because we're putting zero assumptions on F, but that's a lemma. And for some reason, this P is local at the target. And so the proof, many proofs in our library look like this. So we're starting with a without loss of generality block. And for the people that, well, without loss of generality is a tactic in Lean that does what it says it does. It claims that it suffices to show that we may assume this. So under this assumption, we may assume that this theorem is true. Then we do a proof for the general case, assuming it's true for this case. And then we may later use this assumption. And this is very nice because so we get this statement. So we're claiming Y is equal, and this is now an actual equal. Y is a scheme, spec R is a scheme, so this makes sense. And then we're doing some proof using some locality argument. And then after that, we're saying obtain R, refill HY, which means replace Y by spec R everywhere in the proof and forget that Y ever existed. That's quite nice. And we can maybe for some reason do the same argument on the source. And then in the last block, we actually have replaced everything in terms of rings and everything in terms of homomorphisms between rings. And so this is quite nice because it's a clear separation of concerns. We know exactly what's going on in this proof. Here we have a reduction step on the target, a reduction step on the source, and then we have some actual mathematics. So that's this last part is where the AGA proof starts. Yes.
How do you manage to get inequality between Y and spec R?
So we need to check this on an affine cover. So what we're doing is local at target if of open a cover. So we're using the fact that P is local at the target. So we may check it on every open cover. And we can make an affine cover because, as I said, we don't model open subsets as of the form. We don't model open subsets as actual open subsets. We use open embeddings. Okay. So now we can cover it by spec of R's for rings R. So we can actually replace Y by spec R. And this really relies on this bundled approach, because this is, if these were types, this would be an equality of types and would be very badly behaved. But this is just an equality of some terms of some category. So all the structure of Y is transported over the is then spec R. So Y is spec R, and I can now work with spec R and just forget about Y. So this is quite nice. But let's go one step further, namely, so far we've only considered properties that happen to satisfy some locality condition. So we have some property P that we know is local at the target. But we can also do it the other way around, because we can do if you do some algebraic geometry, or if you know some algebraic geometry, then you know this. Many properties, many definitions are even defined locally. They're defined from some local property of rings or from affine schemes. So this is a example definition. A morphism of schemes is smooth, whatever that means, if for every x there exists affine neighborhoods of the source and of the target, such that the restriction to U and V is a smooth morphism of affine schemes. And we don't have to worry about what smooth morphism of affine schemes means. That's just some internal definition, some ring theory definition. But the way it's extended to all schemes is purely formal. It's just saying around every point I have some neighborhood such that the restriction satisfies this ring theoretic property. And so, well, we can put this in mathlib, and this is more or less actually the definition. So this is precisely what I just wrote in LaTeX. And then we can start proving things about this. For example, the composition of smooth morphisms is smooth. And you will realize this is very annoying. This is tedious, and because somehow at every point you have to find an open, and then you have to find an open in the middle, and then an open on the right-hand side, and the opens won't match up, and then you have to restrict things in a smart way. And so there's work that is needed here to show this. And we also have to do this proof for every type of morphisms that happens to be defined in this way. We have to do this for morphisms locally of finite type, locally of finite presentation, unramified, étale, flat, etc. So all of these have a very similar structure. They're all defined by a property like this. And for all of them, we need to show that they are stable under composition, and for all of them, it's annoying. And so, well, what we can do is, right, the textbook proof of this fact is, of course, well, the assertion is local. So it follows from the fact that we already know it from commutative algebra. And so what we can do is we can define a constructor for these morphism properties that takes in a morphism property of affine schemes and spit out a morphism property of schemes, and does precisely what we just said. This is literally the same definition for smoothness, but just for smooth replaced by a P. And now we can, well, you can ask, what do we gain? Well, we gain a very fast definition of smooth, but that's not really the point. And this is not even how it's defined in mathlib, because that's ugly. But smooth is equivalent to an induced property of this form. But what we get is we can start defining meta properties of this P. So we can say, well, a morphism property in some category is stable under composition. Well, if it's stable under composition. So if whenever F satisfies P, G satisfies P, then also the composition satisfies P. And then we can prove meta theorems about these properties of the form, okay, if my morphism property on affine schemes, so my ring theoretic property is stable under composition, then my induced property is stable under composition. And so, right, so I immediately get that smooth is stable under composition from the corresponding property of on rings. And the proof of this lemma is of course still tedious, but we only have to do it once. And you can imagine that there's a whole vocabulary around these morphism properties. And whenever we prove something for rings, we completely mechanically get the statement for schemes by this sort of procedure. And well, we can ask, is this good enough? Well, it's not bad, but I would say there's still room for improvement. And so one of the improvements that we can have is, well, this is just a more or less random proof that I took from the library. You don't have to read all of this. You see that maybe the general pattern is similar, but all of what I marked here that is barely readable, I hope it's visible. So the blue highlighted section, that's all subsumed in the sentence, la question est locale sur Y. So all of this is not happening in textbook proof. And of course it would be great to get rid of these, at least get rid of, it's probably expected to state that we may assume this, but then it would be nice if we could automate this part and this part. So the actual proofs that this works out. But yeah, I guess the good part is that the proofs haven't really grown. So the blocks of boilerplate that we're putting here is more or less constant. And the complexity is increasing. So there's hope that this is really just constant overhead. But if at some point this actually starts scaling, then we need to figure out a solution. Okay. And another part that we definitely haven't solved yet is, well, we have is local at target. I already mentioned that is local at source needs to be defined differently. Well, it has to be defined in this way. I gave it as an exercise earlier, but now I'm spoiling it. So, well, so you need to check it on the pre-compositions. So it's fundamentally different. The restriction to an open on the left-hand side is different from the restriction of an open on the right-hand side. And so for single morphism, we already have two. Well, what about diagrams with more schemes? So I'm just putting examples of diagrams that happen to have multiple schemes. And actually, all of these, well, maybe not the last one, but all of these are reasonable diagrams that can appear in practice. And now you can start saying, well, it's local on S, it's local on Y, it's local on X. And here you can say it's local on T. And for all of these, it means something to be local. And for the reader of an algebraic geometry textbook, it's immediately clear if they say the problem is local on S, they understand what it means that the problem is local on S. It means that we can find a cover so that we can restrict this cover, pull back this cover to X and pull back this cover to Y, and then we can do an argument. So this is not really, so what we would have to do is we would have to define, I don't know, a triangle diagram property, a triangle to inwards morphisms property, and then define is local on the left, is local on the right, and is local at the base. And all of these are different. And so that doesn't scale. And we, yeah.
So I wonder how many diagrams of these kind you actually have in practice. If there's just a finite collection, say do this plane 10 times as opposed to infinitely often.
Well, I would claim that currently the most common diagram is this one, and maybe the one completed to not the unreasonable one like this one, not the circle one, but the pullback square. This is very common. But then you have to reduce on Y, you have to reduce on X, you have to reduce on S, you have to reduce on the pullback itself. So it's already 4. And yep.
So how does it work? Do you refine the covers? Is this the operation internally?
Right. So
you refine covers and
yeah, that's what we do. We use, for example, if we maybe have this satisfies some property that is local at the target, and we want to prove something with this about this map, or so, or we want to prove something about this map, and we need to restrict this diagram, and we want to reason locally on the target, then we would use the locality of the target of this property to take in cover of S, and then we pull back the covers to X and to Y.
Isn't it a filter of covers that you need?
A filter
of covers. I mean, if you can join covers together, a finite number of them. I don't...
You can refine covers, yes. So you, for example, to get the pullback, you can refine this cover and refine it more and more, so that you eventually get nice covers of the pullback, where the components of the pullback covers are the components of the pieces. And this is exactly by refining covers and covers. Does that answer your question? Maybe, I'm
We can talk later.
curious to hear what this filter of covers. Maybe that's a great idea. Okay, so well, one approach, of course, would be we could talk about locality properties of diagrams. So we could take a diagram from some index category J to scheme, and we could state everything about properties of diagrams, and we could say, well, some property of diagrams is local at some point of the diagram. This is, well, possible. The problem is this really needs metaprogramming support. There is no way we're going to we have this concrete situation of two morphisms. Now we spend 10 lines to construct J and a functor out of J to scheme and replace every morphism in the goal with the application of some morphism in J to this functor V. So this is not reasonable. Ideally, we could have a tactic that takes a diagram of this form and produces such a functor. This is something I've tried, but I didn't succeed at. But this could be possibly done. And then we could possibly unify all of this: is local at target, is local at source, locality of objects, and so on. So I have some more details here, but I think in interest of time, I'll skip over them. And well, conclude with some future work. So some of these are ongoing, some of them are really future work. So for example, I would like to generalize all of this local at target to other topologies. So far, we've only talked about open subsets. Now you can also take, well, open subset, we said, are open immersions. So we can talk about étale maps or other maps, smooth maps we've seen before. So this is a generalization that we will need to do applications to étale cohomology, for example. Then develop some concrete algebraic geometry. This is something we're quite bad at, I would say. Develop some actual algebraic geometry that a classic algebraic geometer would call algebraic geometry. So algebraic cycles and divisors. This is ongoing. There's people in Utrecht working on this. Czech cohomology is something that I talked to you already earlier, but so there are multiple people interested in this and working on this. Then there's a project on toric varieties and group schemes, which is very exciting. They use the algebraic geometry library to do toric varieties, which is some intersection of combinatorics and algebraic geometry and convex analysis. And then unfortunately, I can't put ongoing here because it's not ongoing. We have a definition of quasi-coherent sheaves due to Joël, but that's it. No, we don't have anything else about quasi-coherent sheaves. For the people that know algebraic geometry, we don't know that M tilde is quasi-coherent. We finally need to connect elliptic curves to schemes. Elliptic curves are 5 tuple of numbers. They should be schemes. And we need to prove, of course, that these elliptic curves are then elliptic curves in the highbrow algebraic geometry definition. And we could do a Zariski-Main theorem, either elementary or proper, using cohomology. But both of them are, at least the elementary version is definitely doable with what we have, and people could try to do that. And then, of course, cohomology of quasi-coherent sheaves. But that, of course, depends on quasi-coherent sheaves. And yeah, but we need to find someone who does this. Yeah, so anyone who's interested in contributing to this, very happy to talk to you. Also about the ongoing ones or the open ones. If you want to contribute, then ask me or ask Andrew about suggestions. And then let me stop here.
Time for a couple of questions, except Cyril that already did. Okay, so maybe I have a short one. So you said you started, you tried to do some metaprogramming. So what did go wrong? I mean,
so I try to construct these diagrams or these functors from actual concrete objects. And the problem that I didn't manage to figure out how to construct the diagrams is that all the equalities are definitional, are judgmental. So I can construct a diagram that has the correct objects and I can propositionally show they are equal. But to really make this usable and to replace everything by these by this diagram, it would be much easier to show to do this if they were judgmental equalities. Because right now, the proof to showing that this diagram actually represents the objects that are in the context is extremely tedious. Because, well, essentially, yeah, you need to metaprogrammally construct this functor, this diagram. So.
And maybe I wanted to make a couple of remarks. So maybe you want to advertise the thing in Heidelberg for people who are interested in, I don't know if you have a link to that, but there will be a workshop for people interested in formalizing algebraic geometry. Do you remember the dates?
It's in November, mid of November, but I don't remember the dates either. But it's formalizing algebraic geometry and it's targeted at PhD students and postdocs. And it's not much lean knowledge is required. So just some basic lean knowledge is required.
Maybe and I don't have more information. I mean, I've just seen the announcement on the lip, but I think it's relevant. So maybe two quick comments about the differential geometry, the parallel with differential geometry. So of course, the reason why they can get rid of having the atlas or having the data of the chart is because they still remember the structure sheaf. So it's not like they only remember existence of some open cover. They remember the structure sheaf, the sheaf of regular functions. And also, of course, this question of local properties, we have exactly the same one in differential geometry. It's exactly the same way textbooks say this is a local property, so we can assume everything is a vector space. And it's not only about having, the problem is not only about having many manifolds and many maps, it's also that you need to remember that this map is actually a vector bundle. So if your statement is about something happening for every vector bundle over a manifold, and you need to reduce that to an open subset of a vector space equipped with a trivial vector bundle. And so it's not only about the number of maps and manifolds, and I guess it's even worse in algebraic geometry. So it's clearly not so easy to say what it means. This is obviously local. And in the sphere reversion project, when we did differential topology, I mean, half of the project was 3 lines in textbook, and those 3 lines were exactly, and the property is obviously local, so what we did in the local case is not. But going from the local case to the global case was half of the project.
I would be very interested in trying some of this in the differential geometry. I talked with Michael about for immersions. And I think there can be something done, but
we are a bit late, so I would say let's skip for the coffee break. Thank you.
Wait, this, we only see your name now, we don't see the. You're just volunteer yourself with tech work.
And now we can do the PhD. And yay, it works.
Okay, so yes, I'm Niels and I'll be telling you all something about the Unimat rock library. I'll just start with a 1-slide description of what this talk will basically be about. So what is Unimat? Well, basically, as you might have expected, it is a library of formalized mathematics. Okay, and it's based on the rock proof assistant, which might explain why on the previous slide I was talking about rock Unimat. And one of the interesting features that Unimat has that you might not see in other talks during this workgroup thingy is that it is based on homotopy type theory. What is that? Well, I will explain that later. And also one thing that is interesting about Unimat is the kind of results we have, because for instance, in people do a lot of classical mathematics. We saw Isabel today also like various results ranging from computer science to normal mathematics. But what we do is generally a lot of category theory, which of course also is present at other places, but I think we might go a bit further with that in the sense of like we do it more, I think. So what is the structure of this talk? it will basically be guided by several questions or just several words. Who, what, how, why. So let's start with who. Who are the people behind Unimod and how did it come to be? So now we will go back or go to a history class. So how was Unimod founded? And basically it was like a combination of 3 different projects. Like, first of all, like the Foundations project by Vladimir Voivodsky. Second, something by Arends, Kapulkin, and Schulman about rest completions. And thirdly, some project by Dan Grayson about K-theory. They were put together, that was Unimod. And to add some kind of historical context, and that's especially about like the upper left leg. So the Foundations thing by Vladimir Voivodsky. So this is kind of in the time where homotopy type theory was being invented. So already like in the past, people knew about type theory, and Vladimir Voivodsky came with like a revolutionary new idea to consider it from a different perspective that was homotopy based. And I think, I don't know exactly when, but he started to follow like courses on like doing formalization, learning the EuroProofNet system, and he started formalizing his ideas by himself. And he went to proof assistance as a pure mathematician doing stuff like algebraic geometry and all kinds of homotopy theory. So that is basically how Unimod came to be. And by now, the people involved in Unimod is a slightly different collection. So the current coordination committee consists of 7 people, and they're basically the ones in charge, where in charge means maintenance and pull requests. So it's not so much in charge, but we do the chore work. So we're the janitors of Unimod. And this is a bunch of people who are doing this stuff and spread out at different places. So for instance, someone we saw on the previous slide, Benedict Arends from Delft, Dan Grayson from the US, although retired. Then we have 2 students, Arnold van der Leer, Michael Lindgren. And Arno came into Unimod via Benedict because Arno did his master in Delft with Benedict, contributed stuff, and also helped with these kind of maintenance work, meaning that he got the position there. And Michael Lindgren, who did his master, if I recall correctly, with Peter Lamstein, and also contributed to the maintenance of Unimod and was rewarded with a position like this. And Michael and Peter are in Sweden, Stockholm in specific. And then finally, 2 more people, Ralph Matas in Toulouse in France, so not too far from us, and me from Nijmegen. And yeah, this is the current people in charge of Unimod, but there are also other people contributing, like Kobe Willard, the student of Benedict, and yeah. So one thing that I also would like to highlight is like the whole growing the Unimod community, because when you start a library like this, it's quite difficult to find people, and for that reason, people have organized schools. So I think was one of the persons who took a lot of initiative with this was Benedict, and they, so together with other people, he organized a school in 2017, December in Birmingham. Funny thing, December back in that time meant snow, which meant snowstorms, meaning that most people couldn't attend like half of the school because their flight got cancelled, meaning that after that we actually gained census and organized it not when it was snowing. In particular in Italy 2022 in July, which means that it was the complete opposite, like 40 degrees or so. And these schools is also the place where I got to know Unimod. So I joined the first school in 2017, and this is also the time when I learned it and also got in contact with the people involved in Unimod. So that is basically some kind of overview of the people behind Unimod. But it is not just a collection of people doing stuff, it is a library of mathematics, meaning that it has content. So let's look at that content, and I'll start by completely zooming out. So we have a whole big, not so much only a Git repository, but it's like a whole collection of repositories that consists of various repositories. And among those is the ROC Unimod, but I'll also highlight the other repositories in this organization. So for instance, we have like 2 repositories that is about the study of high inductive types. So set hits and groupoid hits, which is what I did during my PhD. So I used Unimat to study high inductive types and in the context of homotopy type theory. But people have also used it for other stuff. For instance, Peter Lamstein, together with Benedict Arendswet, are very interested in like the semantics of type theory. And they made this whole type theory repository in there. Then someone from Paris, who is not here, Ambra Lafont, used Unimat in the context of syntax, like higher order abstract syntax and stuff like that. So these 4 all make use of the ROC Unimat library, but there are also some other things there, like the symmetry book and Acta Unimat. And these are all together in the same organization. So there's all repositories in the same organizations. And it kind of shows that there are quite some there's quite some variety of topics there. And also it is some people doing Acta here. Yeah. But what is in the library? So what is in Unimat, the one that I'm actually talking about? And in this, basically Unimat is organized by having like a list of packages. Each package has some content in it, and that's it. And here I ordered like some of the packages that we have. I didn't include the smaller ones, but basically what do we have? So we're all built upon our foundations. So the foundations is the root of the Unimat tree. And then you can basically see like 2 leaves in it. Like for one of them is more traditional mathematics, where there's stuff like real numbers, periodic numbers, algebra, order theory. But on the other side, you see a much heavier one, which is more on categorical stuff, like category theory, bicategories, homological algebra, model categories, which are like clearly category theory because that's just in their name, basically. And also other things like algebraic theories and substitution system, which might not be obviously category theory, but if you look at their content, they are, because they build forth upon the results in category theory. Like, for instance, substitution system that I wrote very perfectly here, as you can see, is more like a categorical study of syntax. And if you do that categorically, then of course you will be using stuff from category theory. But here you might still get like a feeling of like, yeah, kind of like similar weight, as much normal mathematics as category theory. So let us look at some statistics. So how much percent does each package contribute to the total amount of lines of code of Unimat? And I did the count. Well, I'm not going to count lines of code, but CogWC counted for me. So 39.6% of the code of Unimat lies in the category tier repository. And 35.9% of the code lies in the bicategories repository. Meaning that around 70 to 75, I don't know how my numbers work anymore, is just purely dedicated to category theory and bicategories. And if you then include stuff that is adjacent to it, like, or also basic category theory, like model categories, algebraic theories, homological algebra, and substitution system, you get basically, that's like 80% category theory. So while Unimat is in essence a library for all of mathematics, the numbers do not lie. It is mainly a category theory library. And I also want to basically give some kind of feeling for what it really entails with actual numbers of lines of code, because let's say it was like 200 lines of code, like 39% of that being category theory is not that much. But in fact, category theory and bicategories each is around like 250,000 lines of code. So it's not a small amount of stuff that we have. There's actually quite a lot, I would say. And you can see the difference between the main category theory repository directories versus the rest. They do take most of the compilation time and the lines of code. And to illustrate what kind of stuff we do here, I will of course, I can't give everything. Like, I'm not going to show you 200,000 lines of code. That would not be very fun. I'll just like highlight four things that we've done there. We've done more, but for instance, for category theory, things that we've done are like monoidal categories and monoidal categories with an action, also known as exagories, because some people like swapping two letters to create new words. There's like study on like rest completions, and that's a bit more specific to homotopy typed here, but that's also a topic here, like rest completions of categories, but also structured categories like topocies. And our favorite thing ever, display categories, which is something that is very popular with the people doing homotopy typed here, but has not really been integrated into other places yet, like Lean, probably because they don't like dependent types as much as we do due to automation reasons. Now, by categories, and what are the stuff that we have there? Of course, the classic formal theory of monads by Wall Street, the growth and deconstruction, but then not so much as like only as like going from a vibration to a pseudofunc, but really as a bioequivalence, because otherwise it doesn't really count in my opinion. That's just making one direction is like nothing, basically. The full bioequivalence is the only real thing. Then the basic theory of like double categories and double bicategories is something we've done or worked on recently and finished stuff on. And of course, we're people who like type theorists are very naturally attracted to type theory, because why else are they type theorists? So we also study stuff like semantics of type theory. So we have also theory about comprehension categories and comprehension bicategories. So this is basically some kind of very quick overview of what is in Unimod and what have we been doing so far. And the kind of thing that you see here is category theory, category theory, category theory, category theory. Why do we like this so much? Or why do we like this so much in this particular framework or foundation of homotopy type theory? And that is basically what I want to tell about in the remainder of this talk. So what is the main thing that I want to tell you from now on? First of all, I want to basically give you an idea of what homotopy type theory is. So just an introduction, because not everyone might know. And then I'll argue why I think homotopy type theory offers a better setting to formalize category theory than, for instance, classical mathematics. So if I phrase my talk as a single provocative thing, to just hope that people would like that and would pay more attention, homotopy type theory is better for category theory than ZFC or Lean or whatever. That is basically one thing, if I want to phrase it very provocatively. So let me start with, what is homotopy type theory? So in essence, it's like an alternative foundations for mathematics. So it is an alternative foundation that also gives like has alternative axioms and an alternative view of what it means to be like a mathematical object. And the key aspect of it is the univariance axiom. And that is something that really adds this whole strength to homotopy type theory, because it allows us to treat mathematics with a more refined notion of equality. So rather than always have a equality mean like two things are like exactly the same, that you can really like, we can view stuff up to more like isomorphism. It allows us to have more suitable notion of equality for certain mathematical objects. Together with this is also the view of like types as spaces, and paths as proofs of equality as paths. And there are two aspects where I think homotopy type theory has been most successfully applied. One being synthetic homotopy theory, so that really plays on this whole game of types as spaces. Because if you view types as spaces, then you can just do topology by just saying like, oh, we're doing type theory, and now we have some random type that represents a space that I want to study. That is basically the idea of synthetic homotopy theory. Like you do type theory, but you phrase concepts from homotopy theory as like type theoretic constructs, and you just work directly in type theory. The second being univariate category theory, which is what I'm going to talk about later in this talk. But let me first show in which kind of proof assistance one can do homotopy type theory. And this is where where you can see that we really are friends with each other and that we really like collaborating, because we have like 7 libraries. You might only have 1, which kind of also shows a bit of a challenge, because if people do not collaborate, then this is what you get. So as you can see, there are many options. So first of all, there's a distinction between like the hot and the cubicle world. So people doing like plain homotopy type theory and people doing like cubicle type theory. I won't be talking about cubicle type theory at all during this talk. So I just want to highlight their existence. And the second thing is multiple proof assistants that are being used, where you have to notice this is only for Lean 2 because they threw out the homotopy type theory Lean feature in like Lean 3, meaning that all of the homotopy type theory in Lean is like deprecated and not real anymore. So here you see a bunch of libraries that we have, like Acta Unimat, type topology, Acta Hot, that was, I think, discontinued, but I don't know whether people still work with it, but it exists. You have the Rock Hot, although they didn't change the name of the repository, so officially they're called Rock Hot, but I don't know why they didn't change the name. And the one that I'll be talking about, Unimat. So that shows that you can like implement homotopy type theory in various proof assistants. And what is the idea here? So what is the idea of homotopy type theory? It's this whole game of like types as spaces. So how does this work? So if we do type theory, we have like the notion of like a type, we have the notion of a term. We can make like identity types, so we can talk about equality of terms. And these identity types can be iterated because the identity type is again a type. But we can thus make terms of the identity type, meaning that we can just repeatedly apply the identity type and talk about equalities of equalities. So if you come from like a traditional point of view, you might think, okay, a type is something like a set. Like a type is like the term by its terms, and that kind of feels like a set. A homotopy type theorist says, no, a type is a space. Because while terms are still elements, so points in the space, the difference comes from how we view equality. If you take a kind of set theoretical point of view, you see equality as 2 elements being exactly the same. But the homotopy type theorist has a different point of view. An equality is seen as a path within the space. So these 2 points might be different, but they must be connected by a path. So you're in some space, 2 points might be different, but connected by a path. And that also permits us to have a meaningful or non-trivial notion of equality between 2 different proofs of equality, because there's a homotopy between paths. So who cares about tables when you can have drawings? So let's draw it out. Types as spaces. This represents a space, although it's mainly a circle, but we see this as like some kind of topological or geometric space from which we can pick certain points. Like here, I pick 2 points, X and Y. Well, what does it mean for those 2 to be equal? At first glance, from a set theoretical point of view, you say, oh, no, different. They're different points because look, this is a different place than this. But we can connect them via a path. For instance, we could follow this path P here on top, connect X with Y, and we say, actually they're equal because we can connect them by a path. We could also pick another path, this Q here on the bottom, and yes, we could have a bunch of paths between points. And if we're going to think about what is a homotopy, it is a way to fill in this whole region between the two different paths. So it really corresponds to this notion of homotopy in actual homotopy theory. And this is the way one views types, terms, and identity proofs in homotopy type theory. And it becomes interesting when we view different kinds of spaces. Like, for instance, we can represent the circle as a type as follows. Like here, this is a circle. I did my best to draw it. And here we have fixed a point base here. Well, now, how can we identify base with itself? So what paths do we have from base to itself? First option, we do nothing. That is just the reflexivity path. So base is equal to base, and we take this path. We just stand still, and that's it. But it is a circle, meaning we can also go around, and I don't want to jump, so I don't do the whole circle. So, and we can also iterate that. We can also go around the circle multiple times. We can also go backwards because no one forbids us from going backwards. This is not a one-way road, meaning that we have, like, for each integer, a way to identify base with itself. So rather than having only one way to identify this point base with itself, we have infinitely many. And that is an important observation within this field of homotopy type here, is that identity is proof relevant. We could have proofs that an x and a y are equal, or we could have two different proofs that some x and y are equal. And at first this seems weird, because normally in mathematics, you think of equality, something you can prove, and done with it. You never worry about it again. But if you're working in a setting where these identity proofs don't necessarily have to be the same, then that also gives you some richness. Because by permitting these identity proofs to be different, you can basically enrich this notion of identity that you have. For instance, in homotopy type theory, one can prove that an equality between two groups is the same as an isomorphism. This is an interesting aspect of homotopy type theory. And this is something that actually reflects what one usually does in mathematics. If we do group theory, we generally don't work with groups up to, like, equality in Z of C. That's just weird. No one does that, and no one should want to do that. Instead, we're working with groups up to isomorphism. We're only interested in properties that are preserved under isomorphism. And that is reflected by this feature of homotopy type theory. And in this sense, it more faithfully represents certain mathematical practices. And that all arises from the fact that we're working with a more permissive notion of what it means for two objects to be identical. Of course, we're doing dependent type here, so I also want to show how do we view dependent types in homotopy type theory. For that, we have this drawing. So here we see the X that we know from the previous slides, and here we have some points and some path in it. So how do we view an identity type?
How do you reconcile the fact that you always give the same explanation about groups are up to isomorphism, this is how mathematicians think about groups, with the fact that your library is 80% category theory and no group theory in it? So
yes,
where is the mismatch coming from?
Because I think this, okay, so there are two aspects to this. So first of all, it's a social aspect, because if you have a bunch of people who care about category theory, of course they're going to do that. But I think from a more conceptual aspect, I think these differences or these point become more interested in like a categorical point of view. For instance, when we do category theory, we, first of all, there is like the whole notion of like working up to adjoint equivalence, working up to isomorphism. So if we do category theory, we have like two different notions of equality. Second, when you do group theory, like maybe I don't know group theory enough, that is very possible. I'm not a group theorist at all, but I don't know like any kind of things where you are really like hindered that significantly by certain proofs that where you need to transfer stuff over an isomorphism. I do not know such proofs in group theory, but in category theory, these are things that you meet quite a bit. So I think the point that I was making here I was making about groups, because if I want to make it for categories, then I need to waste 50 slides or whatever, I don't know how many slides, to be able to make my point carefully. For groups, you see the same thing, but I think this principle becomes more powerful if one does category theory. Because when you deal with higher dimensional structures, like categories, you really want a more topological point of view. Does that answer your question? Are there any more questions? Yes?
Sorry, following up on this point. So in computer algebra, a lot of time is spent on switching to an isomorphic presentation of a group in which computation is more efficient. So is that the situation where homotopy type theory would get in the way?
So, okay, so this is something that I think people do have worked on this. Like, I think there is like a paper where I'm pretending that I remember all the authors' names, but I think it was Angeuli, Merten, Zeuner. And what they basically did was some kind of representation independence. So they show like, okay, we have some kind of interface. We have something that's isomorphic to it, then we can transfer stuff from here to there. That is kind of similar to what you're describing. There might be some practical consideration because sometimes you want to have like very concrete implementations. And when you do this transport, because it's defined very abstractly, you don't always get full computational control of what happens when you transfer from one to the other. So it is something that I think people have not explored enough in this case. And I think one thing that's also interesting is like the difference between like concrete versus abstract results. Because for abstract results, it often doesn't matter how stuff computes. Like if you have something that transfers to the other, that might be fine. That happens in category theory a lot when you work with universal properties. So then that works quite well. For concrete cases, that might be a bit less nice because you want it to correspond to a certain representation of something. So it is something where I think there might be potential. It is something that I have not seen explored enough. So I don't know about how much that potential is exploitable in practice. Other questions? Okay, so homotopy type theory is based on dependent types. And if you want to do dependent types, you also need to understand dependent types. And I just wanted to make the drawing of dependent types. So we view dependent types as vibrations of spaces. And how we think of this is that on the bottom, we have the space X that we've already seen, or I added points X and Y to it. And on the top, we have a space Y that I do not draw as a single space, but rather in terms of its fibers. So for each point here, we have a fiber above it. So for X, we have the fiber YX, and for Y, we have the fiber YY. So we think of a dependent type as a space above another space. But this must be suitably behaved in some way, meaning that whenever 2 points X and Y are equal, meaning that we have a path going from X to Y, then we can make a function above it, like this transfer function that sends YX to YY. And this is some concept known in topology as a vibration, and that is how one interprets dependent types in this setting. So what is the whole key feature of homotopy type theory? That's the univalence axiom. And I will basically describe it a bit faster than I've been before. So what does the univalence axiom say intuitively? So we can talk about equality of types, and we can talk about isomorphisms between types. And this notion of isomorphism is defined as something like a bijection, meaning that for all y, we have a unique inverse image. And what the univalence axiom basically says is that isomorphism is the same as equality. So if two types are isomorphic, then they have the same properties, which is not the case in set theory, where if you have an isomorphism between two types, then you just know they have the same number of elements. And this is the key axiom of homotopy type theory. So how can we imagine this? We have types and functions. So here on the bottom, we have like collection of types. On the top, we have like all functions between them. But we have an interesting notion of equality between types, which is represented by pods. And what we basically the univalence axiom says is that the pods of types are determined by the functions. So pods of types are completely determined by the functions because they're the same as equivalences. So I also briefly want to discuss the notion of a homotopy level, because you can characterize types by how complex their identity types are. Because if you do homotopy type theory, there still are types that are kind of like sets, because there still are types whose identity type is trivial, like the natural numbers. One can prove that there's only one proof that two natural numbers are equal. And you can make a whole classification of them, like you can define one types, whose identity type is not as simple as sets. It's still more complex, but there are types for which like homotopies are trivial. So we have points, we have pods, and the homotopies are trivial. And you can make this as high as you want. 2 types, 3 types, whatever, n types. And one can see this as follows. So if we do normal mathematics, then this is often what we see. We just see the world of sets, like Booleans, rational numbers, integers, reals. That is represented in homotopy type theory via a set. But when you do structures, you already see some difference appears. Because in mathematics, we would still see them as sets. In homotopy type theory, they would not be sets. They would be one types. Because identity of groups is the same as isomorphism, meaning that groups have a non-trivial identity types. I can push this further up, for instance, to categories. And category theories have a more complicated identity type, but still not like fully, still is like a 2 type. So the difference is that from the perspective of normal mathematics, we generally work here and we talk about objects here. But homotopy type theory allows us to get objects with like a higher homotopy level, meaning that we're not restricted to stay in this world, which is what one would do in like Lee and Isabel. We can also enter these kind of other things. And the reason why we use this is because there are advantages of using homotopy type theory when formalizing categories. And this is a part where I think you can actually see advantages of homotopy type theory. I think you see this less in group theory, but that might also be because people don't do that much. And there again, you could have like 2 different reasons. Either people don't do it that much because they don't care, they don't see interest opportunity, or because we don't have enough time and we have other things. But category theory is a place where I think we can see it being successfully applied. And in essence, there are like two aspects to it. So one is more conceptual and one is more practical. So the conceptual aspect here is that when we do category theory, we generally do not want to work at all with some strict notion of equality that is offered by set theoretic foundations. That's just wrong in category theory. It's like, doesn't make sense. But we still have like two interesting notions of indiscernible between categories. Because either we work with categories up to adjoint equivalence, which is what we usually do in like 99.9% of the time. And we can work with categories up to isomorphism, which is something we generally do when we work, for instance, at like models of type theory, because there we are forced to work strictly. And the way we normally deal with this is just by shouting our morals to each other. It's like, you're a bad person, you use isomorphism, that is not good. You should work up to adjoint equivalence. Even going as far as people saying like, don't be evil as real things on NLab, saying it's pure moralism how we deal with it. It is purely saying this is not good. But homotopy type theory offers us a more precise language that allows us to not only refer to moralism, but also to logic to distinguish these two ways of doing category theory. So rather than being a bunch of moralists, we can actually be logically precise. So what is going on? How can we do this? Let's start with the notion of category as one would usually do. We have objects, we have morphisms, identity morphism, composition, usual laws. This is what one would usually say is a category. And the interesting aspect here happens at the fact that we have a type of objects. It happens at the fact that types would have a non-trivial identity type in homotopy type theory. Meaning that here a category is not something like this, but something like this. Between objects, we have an interesting notion of equality between them. So we have an interesting notion of paths. And if you look at this like semantically, you can say, okay, this does not correspond to categories in ZFC because it has more structure than that. Because we have this extra stuff here that we do not have in a normal category. How can we fix this? How are we going to fix a situation where we have too much? Two possibilities. Either we just say that part is trivial, we just cut it off. And we say it doesn't really matter, it is just trivial. This is the notion of set category, which basically represents doing category theory up to isomorphism. It's something you can make precise. Identity of set categories is isomorphism. The other way is by saying, well, actually this information of the paths was redundant because it was actually determined by the morphisms, which gives the notion of univalent category. So first, what is a set category precisely? It is a category where the type of object is a set. Who cares about words when you can have images? So what do I mean with this image is this part is trivial. So this is kind of like not really there. It's completely trivial because all possible paths between objects are the same, meaning that this doesn't really provide any information. The second way is a univalent category, where you say this part of paths is determined by the morphisms. I'm not going into the definition, but I'll just show the picture. So objects, morphisms, paths between objects. What can you do is you can say, okay, we always can map a path to a morphism. Every path gives rise to an isomorphism because identity isomorphisms. And you say this is an equivalence, meaning that the paths between objects are determined by the isomorphisms. And that basically gives us a way to do category theory up to equivalence, up to the weaker notion of identity that one usually would do category theory with. And we can make this actually precise. Like it's not only vague blah, 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 it is real mathematical theorems. One can show that identity of set categories is the same as isomorphism, and identity of uniform categories is the same as adjoint equivalence. Meaning that these two different styles of doing category theory is not pure moralism anymore, it is real mathematics. It is something that you can just indicate by using the appropriate notion of category. So you can also do stuff for functors, okay, good for you. And now I want to talk a bit more about this uniform principle for categories. Because what does this entail to? Let's just look at the categories. Okay, we have the pods between them, let's ignore the names. Every pod gives a functor, in fact, an adjoint equivalence. Same thing, yay, we're happy. What does this allow us to do this? Equivalence induction. What this basically means, to prove for all C1, C2, for all E, for all adjoint equivalence E, we can just prove this for the identity. So when we have a universally quantified statement over all equivalence, we can just do it for the identity. And that simplifies stuff in two cases, and now the laptop dies. So yes, this is the end of the talk because I can't move anymore unless I get technical support. I'm looking at the technical support. The screen is black. So, okay.
Since you are out of time anyway.
Yes, that's fine.
Just tell the conclusions.
Okay, two things that I want to highlight. One, what are things to simplify with this? Is characterization of adjoint equivalences. There are several examples of it, like pseudo functors, pseudo transformations, pointwise adjoint equivalence. And the other thing that you can simplify is like transporting stuff along adjoint equivalence. Like for instance, locally Cartesian closed. If you want to show that's preserved on adjoint equivalence, complete hell, don't do this. And here's a one-liner. Done.
Thank you. Any question? It's not. So since we are at the coffee break time and we are already a bit late, let's move question to the coffee.
Yes.
Thanks.